We've all been there, right? Staring at a line. It could be the grocery store, maybe the coffee shop, or even just a website that's taking forever to load.
Mm-hmm.
And that fundamental rule always seems to be universal. First come, first served. First in, first out.
Right. But it's funny, as simple as that idea is in, the real world, translating it into the digital world is a whole different ballgame.
How so?
Well, you're not measuring time in minutes anymore, you're in nanoseconds, and you might have millions of requests all piling up at once. That simple line suddenly becomes one of the most critical blueprints in all of computer science.
It really is. And today, that's what we're doing, a deep dive right into that blueprint, the Q abstract data type, or the ADT.
It's the concept that dictates the order of operations for, everything from printing a document to how a massive server handles requests. It's really an exercise in system stability.
So our mission today, for you, is to dig into the source material, some foundational texts and these practical coding challenges, to really understand the core rules that govern these digital waiting lines. We want to see where that simple first in, first out rule starts to break down.
And discover the performance trade-offs that, frankly, separate a stable system from a crashing nightmare. We're going to be looking past the code itself and focusing on the policy.
The policy.
Yeah. What defines a queue isn't the programming language it's built in, but the set of rules it promises to follow. That promise, that behavior, is what we call the abstract data type.
Okay, let's unpack this. So if the ADT is the promise, what exactly is the promise of a standard queue?
The promise is strict adherence to the FIFO principle. First in, first out.
No exceptions.
No exceptions. Think of the ADT as the blueprint, right? It defines the behavior you need regardless of the building materials you use. It's just a definition of required actions.
And that distinction behavior versus implementation, that's so critical for you, the learner, to grasp. I mean, you could build a house out of brick or wood, but it still needs a foundation, walls, and a roof, right?
Exactly. So what are those essential operations, the rules that define the queue ADT?
Let's get into it.
Okay, so there are 4 primary operations that have to exist no matter how you build it. First, you need init. That just initializes the queue.
It opens the line for business.
Basically, yeah. Second, you have insert. This is how a new person or a new piece of data gets into the waiting line. And critically, they have to go to the back, the tail of the queue.
Got it. To the back of the line.
Third, and this is the vital FIFO rule in action, is the remove operation. This function has to remove and return the element at the front of the line, the head.
So the one that's been waiting the absolute longest.
Precisely. New items queue up at the rear. The oldest item leaves from the front. It's classic traffic flow.
Okay, and the last one.
And finally, you just need a simple isEmpty check. It tells you if the line is holding any elements at all. Those 4 things: initialize, insert at the back, remove from the front, and check the status. That's your queue ADT.
Now, here's where the theory hits reality and where the source material gets really interesting. It points out that you can implement this ADT using a built-in Python list. But that's a terrible idea, isn't it?
Oh, it's disastrous if you're building a system that handles any kind of real load. It all comes down to performance.
Okay, so what's the problem?
Well, if you use a standard list, inserting at the end is fast. That's fine. But the ADT's rule says you must remove from the front. And in most programming environments, including Python's list, removing an item from the beginning forces every single other element to shift.
Wait, you're kidding. So if I have a queue of, say, 1,000 items and I pull the first one out,
1,000, a million, doesn't matter.
the entire 999 remaining items all have to move one slot forward in memory.
Exactly. That operation is incredibly expensive. We call that an idle operation.
Meaning the time it takes increases linearly with the size of the queue. And
Right. If your queue gets long, your system it grinds to a halt trying to manage the line.
that makes so much sense. So if the basic list is a performance trap, what do developers use? What's the quick, robust fix?
That's where you turn to specialized structures. For anyone in Python, the efficient built-in alternative is DEC. It stands for double-ended queue.
And what makes DEX so much better?
It's optimized under the hood to handle adding and removing from both ends, front and back, in what we call constant time, or OA time.
So no matter if you have 10 items or 10 million, the time it takes to pop that first item off is always the same.
Exactly. No massive re-indexing penalty. It's really the essential tool if you're building a high-performance FIFO system.
That technical detail feels like the core takeaway here. The ADT is the rule, but choosing the right implementation like DEC is the difference between a system that works and one that just creates a bottleneck.
For sure. Now, let's pivot a little bit and talk about the rules of the line itself. So far, the rule has been strict arrival order. First come, first served. But sometimes, that's just not the most logical way to handle things.
Right.
This overarching rule that determines who goes next, we call that the queuing policy.
Okay, so this is where we break out of that coffee shop analogy. Sometimes someone needs to cut the line. Maybe they have a medical emergency or, maybe they're just carrying a platinum card.
Exactly, and in the digital world, changing that policy gives us the most flexible queuing rule there is. Priority queuing.
So how does a priority queue fundamentally change the game from FIFO?
In a priority queue, every single item gets assigned a specific priority value, and the rule changes completely. The element with the highest priority goes first, regardless of when it showed up.
So a high priority task can just jump ahead of a million other tasks that have been waiting for hours.
It can, and it does. What's fascinating here is that the priority queue ADT, it actually keeps the same external interface. You still have init, insert, and isempty.
So from the outside, it looks the same.
It looks identical. The only function that operates differently is that crucial remove function.
I see. So the difference isn't in what the structure does, but in the internal policy that dictates which item gets picked when I call remove. The system isn't looking for the oldest item anymore. It's looking for the most important one.
Correct. When you call remove on a priority queue, the item you get back is the highest priority item in the entire queue. It's almost certainly not the first one that was added. And this adds a whole new layer of complexity because now you have to define what highest priority even means.
And the sources gave some great, really contrasting examples of this. It shows how context completely defines priority.
It really does. I mean, if your queue holds names, maybe priority is just alphabetical order. If you're tracking tasks, it could be a number 1 to 10 for urgency.
Or, I love the sporting examples, if you're tracking bowling scores, the highest score wins. So the highest number has the highest priority.
Right. Higher score, you get processed faster, but then you switch to golf and the whole thing flips on its head.
Because in golf, the lowest score wins. So highest priority suddenly means the lowest numerical value.
That duality is perfect. It shows that the meaning of the priority value is entirely relative to the problem you're trying to solve.
It's such a great mental model. And this is reflected in how we actually design the data. The source material talks about using something like a dedicated golfer class object, which would neatly package the name and the score together.
And that score then becomes the key that the priority queue uses to make its decisions. It's clean. And just like we solved the performance issue for the standard queue with DEC, there's an optimized tool for this too. If you're implementing a high-performance priority queue in Python, you should immediately reach for heap.
Heap. So it's another built-in module. What's it doing under the hood to make sure that highest priority item is always ready to go?
It uses a data structure called the binary heap, which is just fundamentally efficient at keeping a list partially ordered. A heap makes sure that the highest priority element is always at the root, ready to be picked. So that remove process becomes incredibly fast.
Another constant time under operation.
Exactly.
Here's where it gets really interesting for me. If heap exists and it's so efficient, why would a developer ever bother trying to build a priority queue from scratch using something complicated, like a sorted linked list? The source material brings this up as a key challenge.
Right, and that challenge is there to force the learner to confront the hidden costs. When you use heap queue, the system handles all that sorting logic for you. But when you build it yourself, you have to decide when you want to pay the time penalty.
Okay, tell me more about that trade-off. What penalty?
Okay, so let's say you want your remove operation to be instantaneous. Over time, to guarantee that, the highest priority item has to be sitting right at the front of the list ready to go. And the only way to ensure that is to keep the entire underlying list sorted at all times.
Wow. Okay. That sounds like a massive headache. So every time a new item arrives, you can't just tack it onto the end. You have to, walk down the whole list, find the exact right spot for it based on its priority, and then splice it in.
That's it. And that insertion process, finding the right spot, that becomes an operation. So with this implementation, you are knowingly making a choice. You accept slow insertion, which is a dollar saving on dollar, in exchange for lightning-fast removal, all of the dollars.
So it's the complete inverse of that slow basic list queue we talked about at the beginning, where removal was the slow part. This entire exercise really boils down to one question. Is it faster to find the element when you insert it or when you remove it?
Precisely. And the correct answer depends entirely on your system's load profile. If you have tons of new tasks coming in all the time, but you only process them sporadically, you might prioritize fast insertion.
But if your system is constantly clearing a backlog, just removing tasks nonstop, then you need fast removal and you're willing to accept that insertion might take a bit longer?
That's the trade-off. And this knowledge isn't abstract. It defines how real-world systems handle enormous amounts of traffic. The source material even references some specific problems that show exactly when you need FIFO versus priority.
Right, like the bank queue problem.
The textbook FIFO case. Customers have to be served in the order they arrived. That's the rule. That's fairness. If you started prioritizing people based on their account balance, it would be chaos.
So bank queue is a strict FIFO problem. You'd use DEC or something similar.
Now contrast that with a problem like disastrous downtime. Imagine a huge e-commerce server crashes. Suddenly, hundreds of thousands of user requests, purchases, searches, logins are all dumped into a processing queue.
In that scenario, fairness by arrival time is completely out the window. You don't care who clicked first. You care about saving the business.
Absolutely. You would implement a priority queue. You'd prioritize mission-critical tasks first, restore the core functions, process any purchases that were already in flight, and you'd delay low-priority stuff like updating personalized recommendations.
So the priority value there is just pure business importance. It's fascinating. The decision between those two ADTs is literally the difference between a smoothly running service and a failing one.
Or look at the complexity in something like Ferry Loading 3, which has to manage multiple lines and time constraints. You might have a main FIFO queue for regular cars, but a tiny priority queue for emergency vehicles that have to get on board immediately. Real systems often integrate both policies.
So to recap all of this for you, we started with the standard queue. It's defined strictly by arrival order FIFO, just like a physical line.
And then we found the priority queue, which is defined not by arrival, but by some assigned value. It lets system designers override that idea of fairness in favor of efficiency or importance.
If we connect this to the bigger picture, the real power of these abstract data types is that they're defined by their behavior, by their policy.
Yes. You have to identify the correct queuing policy you need for the job. Is it arrival time or is it importance? Before you even write a single line of code, the policy drives everything.
So what does this all mean? It means understanding the hidden operational costs of your implementation is just as critical as picking the right policy. If you have a FIFO problem, you must use a structure that's optimized for fast removal from the front.
And if you're solving a priority problem, you have to define a meaningful priority and then use a structure, like a heap, that ensures that highest value item is always instantly accessible.
Okay, so here's a final provocative thought for you to chew on, building on that implementation challenge we talked about.
Remember that choice fast insertion or fast removal. The most robust systems often have to balance both. So when you're designing a new application, think about which event will happen more often. Will you be receiving more new requests, or will you be processing more existing ones?
That simple ratio, that should guide your decision. It tells you whether to accept the higher cost on the way in or on the way out.
And that decision is what ultimately defines the right tool for the job.